Okay, I think we can start right about in a few seconds. So thank you for coming. Next up, we have MacLemon, who tried to make, and well, he did make more slides than presentations about the USB thing from previous years. So let's welcome MacLemon, who's going to tell us stuff about encoding.
Okay, hi. I'm MacLemon. My pronouns are he, him on Yega. You'll find me on the internets, and in the evening you'll find me behind the karaoke mixer. If you want to post on social media as usual, please use the BalCCon2k25 hashtag, and encoding WTF will go into the W, the T, and the F. So welcome to the philosophy, psychology, and biology track at BalCCon. You cannot not communicate, said Paul Václavic, because every behavior is a form of communication, even if you try to not communicate. This is why operational security is really hard, because if you don't send a message, you're still sending messages. So, disambiguation. So what is this about? And more importantly, what it is not about? Representation matters, and encoding is about representation and making information and data understandable and usable. It's not encryption, because that is about security and making sure that only people you authorize can read a message, or at least that's the intention. It's not compression, because that is about efficiency and reducing message sizes. So what's the purpose then? Well, why do we do encoding? Because of consistency. Data is interpreted the same way across different devices and platforms or individuals. But wouldn't that be in part encryption as well? Because consistent messages can be decrypted, inconsistent ones cannot. Well, yes and no. But yes. Efficiency is for minimizing size and storage and optimizing performance. But wouldn't that be compression? Well, yes and no. But yes. And it's about safety, allowing messages to be transferred without corruption or loss. But wouldn't that be redundancy? Well, yes and no. But that would be redundant. So when did this encoding thing start? This is the sporting part where you get to move. 1990, raise of hands. Who thinks encoding started 1990? That's just 20 years ago. Okay, I see no hands at all. How about the 1st of January 1970, otherwise known as the beginning of time? 1, 2 hands, 3. Okay, just a few. 1961, oddly specific. 1, 2, 3, 4 and the maybe. Yeah, no. How about the 1700s to 1800s? A little broader, okay, a very few more. You already had a vote? Yeah, okay. Mm-hmm. The answer is looming here. Well, as in IT, it's always, it depends. But what does it depend upon? Well, let's look at the building blocks for encoding and what we can build from it. There's a sign. That's anything that conveys meaning. A word, an image, an object. A logo is a sign, a symbol is a sign, a letter, a character, a picture. In the broader term, anything that conveys meaning. We have code. Code is a set of rules or conventions that convert information from one kind to another. Any kind of information. There's encoding. So what is it then? Well, encoding is the process of converting one kind of information to another kind of information by applying that set rules. The existence of encoding mandates the existence of decoding, and that is the process of converting that information back to its original form. More or less, maybe. Can you see any challenges with decoding? Well, just because I saw the sign and it opened up my eyes, I saw the sign. Life is demanding without understanding. And meaning doesn't exist solely on its own. So how is meaning made? There's the study of semiotics, which studies how meaning is being built, how we process signs. It's all semantics, isn't it? I mean, it's always clear and logical what a sign means. Or maybe there is some ambiguity? Syntax. Syntax gives meaning a form, rules how we can piece together individual signs and form a larger entity of meaning from them. If you think about grammar, that's a good association. And then there's pragmatics. Meaning never exists in a vacuum, which sucks. Yet, the same sign can mean different things in different situations. It all depends on context. Context applies implicit meaning to a sign. It can reduce the possibilities of interpretation of a sign by ruling out meanings that just don't make sense in a given context. For example, let's take the German word das Gericht. It can mean a court of law. It can mean a dish at a restaurant. Yeah, German. So what's more likely to be the correct meaning depends on the context, because one might make a lot more sense than the other one. For example, at a certain location, a physical place like a restaurant. It can also be a situation. In the morning when you walk up to the barista and have very sleepy eyes, don't say a word and they'll ask you, coffee or mate? There's convention. This is how we do it because everyone else does it like that. And everybody else surely includes every person. Who the fuck is Alice? You may ask, but if you're Bob, you certainly know who Alice is. Together, all these things, they form something called a semiotic system. We're surrounded by them everywhere, all the time. We learn about these signals and social protocols and all these systems for all our lives. We never stop, but maybe at some point. So, what are some use cases for encoding? Depending on your intentions, you may choose a different way of encoding things. Will you need lossless encoding, something that guarantees that you can reconstruct the original information exactly as it was before? So it's vital to be correct. Because technology changes all over, and archiving is a thing that is very complex for archival. You want to make sure that the original thing can be preserved pristinely. Because do you want your data to stay a while or stay forever? Or is lossy encoding just good enough? Can you remove some data, lose it? Because what you can reconstruct is good enough. Of course, decoding is subject to interpretation, not only with human language, but also with technical protocols, which can be regarded as a kind of language. Loss can occur at any of these stages in the process. So, means to encode. There's very abstract ways of encoding things for us humans. So, what is there in applied encoding? There's visual encoding, stuff we can see. Blinking lights, or a pattern of a blinking light. An LED blinking red, but you know, it should be solid green. An ambulance on its way to an emergency. There's pantomime, which visually encodes emotions, while not being tied to any human language. There's gestures, like, hi, you're welcome. Or, I've run out of fucks to give, please leave. There's acoustic encodings, things you can hear. The sound of a motor or engine revving up. That former ambulance where you've seen the blue lights blinking and you hear it coming and going, it makes a different sound because of the Doppler effect. And you also know that the video encoding job on your laptop is done because it goes silent. There's alarms, your phone going off in the morning way too early. There's blackbirds sitting in a tree imitating the sounds of e-scooters so they make when they're dragged away without being booked. You remember perhaps the Nokia ringtones that birds made? Well, that's so 1990s. Really. Has been observed in Germany, in China, with blackbirds and e-scooters. Real thing. Humans encode sounds about their bodily functions. Or your neighbors having fun. Or voices singing at karaoke night. And what's that smell? Well, it might encode information about something being edible, like a piece of ham. Your nose is a terrible sensor for smell. If you have a cat, you might proxy that. And if the cat goes, you might not want to eat that piece of ham. On the other hand, if you have a dog, the dog may eat the ham to protect you from ingesting something inedible and unhealthy. And it's also nice to know when dinner on the grill is ready. Or if you've grilled other things like a capacitor in a low power supply that just burned out. Who doesn't like the smell of burnt electronics in the morning? Yeah. No, I did not. Don't raise your hands. Also, there's love in the air. Every sight and every sound. And pheromones and other olfactory information is there. It's crucial for mating of many species, like bees, wild bees. And there's orchids, beautiful flowers that mimic the aesthetics, the shape and color of a wild bee they want to attract. And also spread a pheromone that tricks the male bee into thinking there's a mating partner there. And then they try that with the orchid and spread their pollen. So that orchid is pretty tricky, huh? Yeah. There's also thermal information, because sometimes I need some hot stuff. And the weather conditions can tell me if it's cold or warm outside and I should get a hoodie from BalCCon. But humans can only sense a very small range of temperature, 25 degrees Celsius plus minus something. Not very good. Temperature can tell you about something about your phone. It's fast charging because the battery is getting warm. Or the CPU and GPU are getting warm. Did I really open that link? Yeah. It can also tell you about the existence of something. An implant of hardware, because that one plug connector is getting warmer than you expect it to. Might look like this. I swear it's not all black pixels, really. I know you can't see it. It's not on the visual spectrum, but if we look at infrared, there's your hot dog eating your ham. With a healthy cold nose. There's also spatial encoding, because when the dog, a thing is in a certain place, it can tell you something about it, like the time of day, the hands on an hour, on a clock, it will show you. Or that bright giant pixel in the sky, because maybe tonight the creeper's gonna steal my stuff again. It can tell you about the importance of things. Or will you be able to find all your icons on the desktop if somebody sorts them by name? Your body also has something that tells it the relative position of your limbs in relation to your body. You know where you are for the most part, usually. Maybe not after Vacuolix. This is also known as muscle memory. If you hit a certain button multiple times, you will know where that button is without looking at it. This is why we can drive cars without crashing all the time, because we know how to use a shift gear. That's something US Americans don't know, but this wobbly thing in the middle. Yeah? You can recall that position in space and you can use it again. This is also why we have tactile information. It's all getting touchy now. Fingering on a keyboard. It's called Fingersatz in German, yeah? Fingersatz. Those little nubbins on the F and J key, or on the digit 5, if you have a number pad. You don't need to look at that. You can just adjust your position of the hands, and then you can start touch typing, if you can touch type. There's also Braille, these structural bumps for writing that you can read with your fingers. Catch? Or if you have a LiPo battery, that is becoming a fire hazard. You can feel that it's becoming puffy and like a cushion. Huh? Yeah. There's also music, the sound of music. You can record a waveform with microphones, but does it represent all the information of music? What about separate instruments or singers? If I can feel the rhythm of the night, oh yeah, that's vibration. And hearing impaired people, they can experience music by feeling the vibrations. And you can do too, because it's all about the bass, There's notation systems for music, and a lot of them. You might recognize this one. And I bet some of you can hear this sheet music. Ba-ding! That sound also carries memories and emotion in many of you, I guess. You might get goosebumps. They're tactile. You can feel them on your skin. There's facial expressions, because you're having emotions, and it's a good thing to have. Learn about them, embrace them. Emotions are good. For example, when that round peg, yes, it also goes in the square hole. And of course, if you use emoji in chat. If you want to learn more about emoji, BalCCon2k25. Yours truly. There's motion. That's not a non-electrical version of emotion, because it's movement. For example, traffic control. Wait a bit. Come. Speed up. There's a trajectory. If I throw something at you, you can probably approximately guess where it's going. I know you can catch, but you don't know if I can throw. So there's some element of surprise probably. And if you sit on an office chair, you spin me right round, baby, right round. You'll know if that angular momentum changes. Also works for linear acceleration. Office chairs are very versatile in that regard. So let's combine more of those motion concepts into dance. Dance, I said. It's movement. You can learn the moves by observing them. Dance is encoded as motion. It's visually, yes, it's catchy. The leading part also communicates which figure may come next, with very subtle movements that an outside couple cannot see. But it's still movement. You can make a diagram of the necessary steps. That works for ballroom dancing, maybe for a line dance. A whole jazz dance choreography might be complex, but it's certainly good enough for avoiding sandworms. There's also ways to announce the steps for dancing. For example, in square dance, you have 4 couples that need to be synchronized together, but they cannot touch each other. So they have an announcer that tells you which figure's next, and they also have a way to synchronize the couples again, should they deviate. Grand square. So, have you been exposed to encoding in your childhood? Raise your hands. Have you been exposed to encoding? Okay? To those unsure, are you really sure? Huh? How about painting by numbers? Huh? Yeah. This is encoding art by digits, by numbers. Grab yourselves, there's colored pens if you need one, to paint your own. This was invented in 1923 by a person called Dan Robbins. There's also something we're familiar with, which is human language. Most of us are human, I assume. I have not checked. And human language can be encoded in many ways. Raise your hand if you're a person that is comfortable having a simple conversation in more than a single language, like your first language and one more. 2? Well, that's a lot. That's about 70, 80-ish%. 3? Becoming fewer. 3 languages, yeah. Well, like 20 people still. 4? Whoa, okay, 1, 2, 3, 5 or more? Okay, you're showing off. Rightfully so. Yeah, spoken languages. They come in regional dialects, in variants, in accents like German, and Austrian German. Two people separated by their common language. Well, don't go into Schweizerdeutsch, Swiss German, no. There's also sign language. The German word for sign language is Gebärdensprache. It's different from gestures and pantomime, and Gebärde translates to sign in English. You'll see why that is a problem. Sign languages are natural languages that have evolved naturally over time and can be used to express everything and anything, also in a linguistical sense. For example, the Native American people, they developed a sign language for trade because they had their own spoken languages which were incompatible with each other among the tribes. But they used a common sign language for trade, which they still use today. There's also signed languages, or in German, Zeichensprache. They're distinct. Zeichen also translating to sign in English, which does not help with explaining anything. But they're domain specific. They have a very, very limited vocabulary and a very limited amount of symbols. For example, if you go diving, like this water thing underwater, yeah, you can convey like, I'm okay. Yeah? You can also say, I'm running out of air. You can say, baby shark, baby shark. But you cannot have a meaningful conversation about 3D printer kinematics. You also don't need to. So by packing a lot of context into a domain-specific language, you also make it very efficient. You compress it down by encoding it. It's so complicated. Okay, there's written human language. Anyone know a person who can write? I see 1, 2, 3. Okay, well, there's some room for improvement. We'll see. Well, if you write things down, depending on your handwriting, other people might be able to read that, or future you might be able to read that, depending on how distant that future is. But you can read that note back. And things that happen when you know more than a single human language are things like code switching. Code switching usually happens mostly intentionally when you're more proficient with one language, the main language, the matrix language, and one additional language, or more. For example, you start a sentence in one language, und dann machst du ihn in einer anderen Sprache fertig. So you switch it, sentence at grammatical boundaries, and usually intentionally to emphasize something, to express that you're belonging to a group, or to keep some information from a certain person, because you know they don't understand Serbian like me. Or many other reasons. There's a simpler version of that. It's called code mixing, which is less intentional. It's not about putting CSS into HTML. Technically, that's similar in concept, but code mixing happens, for example, with children growing up bilingual with their parents. They just substitute a word from another language because they don't have a concept of what a language is. They're still struggling with words and use the first one that comes to their mind. They mix. That's fine. Or if you want to express something very particular, very pristine, and you know that other word just perfectly pins it, and I cannot do that, I just use that word because it matches better. That's a very different concept, but yeah. There's also very evil false friends coming from that. False friends, they're the same word, it's written in the same way, the same capitalization, nobody lost some trema over the umlauts, yeah, the dots. They're totally the same word, but they have a different meaning. And you will also experience technical difficulties by that. If you use autocorrect and use multiple languages, you may experience something like Verschlimmbesserung, which means correcting something to be entirely wrong. Yeah, it's never duck, I insist. So what if we take all of the above and put another layer of abstraction on it to encode it one more time? Mostly written language. Morse code has an audio encoding. You can hear it. It also has a textual encoding because you can write dashes and dots. It's a way you can hear and write it down without understanding and decode it later. Like a buffering, basically. There's also visual encoding used by scouts and ships. I don't have any of those with me today, and I will not blink at you because somebody might have an epileptic seizure and I don't want to risk that. There's also a spoken version of Morse code. You can speak out the dit and the das and the da. Yeah? It works. It's not very efficient, but for learning, everything goes. Technically or mathematically, this is a Huffman code, meaning symbols that are used very often in a language, like the letter E, get a very short symbol. It's just a single dot. And letters that are less frequently used get a longer symbol. So encoding, again, makes things efficient. Weird concept. But it's not really compression. If you want to learn more about compression, see my talk at BalCCon2k25 about compression. Yeah, so how do computers use encoding? Well, mostly binary. Binary encoding, the notation was invented by Gottfried Leibniz in 1689. So much about new concepts in IT. You take 3 bits to represent the numbers from 0 to 7 in decimal, and you can represent an octal system. Where do you use octal these days? Sysadmins. Permissions, exactly. Change mode, setting POSIX permissions and ACLs. That still uses octal encoding. Optional, but you can use it. If you want to go higher than 7, like decimal, we need more bits. Luckily, bits are relatively cheap to get. It's a system called BCD, binary coded decimal. Yeah, you take 4 bits, and you can represent the digits from 0 to 9 in decimal. The rest of the space is wasted. You just don't use them. It's not very efficient. If you need 10 to 19, well, you need more bits. You take another nibble, or one 8-bit byte. Yes, bytes have not always been 8 bits. History. And you're still wasting a lot of bits. So people came up with Hertz and Chen-Ho encoding methods to cram 3 digits into 10 bits instead of 12, improving 20% of storage there. Interesting. If you need hexadecimal, like more digits, you can go by with 4 bits, and you can encode numbers from 0 to 9, and then you're running out of Arabic numeral system signs. So we substitute with letters A to F, and can go from 0 to 255. Otherwise known as an integer overflow to the Swiss train operation services, which count axles, and the train must never have exactly 256 axles, because it will overflow the counter. It's also very hard to build such a train, I checked. So the question arises, what is a bit? Let's go on a mathematical side quest here. It's a portmanteau of binary digit. And now, please raise your hand if you agree with the following statement. A bit has exactly 2 states. Okay, people expect trick questions from me. There's very, very few hands there. Yeah, okay, maybe 10%. Okay. Okay. Most bits have 2 states, okay? Just like gender is non-binary and most people agree to that, so does biology. What's true for naughty bits is true for most bits on computer bits. So some are 0 and 1. If you use a database to store a bit data type, quoting from the documentation, a bit is an integer value that accepts 0, 1, and null. So a bit is an integer with 3 states. And depending on what type of database you use, a bit may also be a string, a map, a field, a small int, or not existent at all. So what is a bit? Can someone tell me? Okay, we'll classify bits by purpose. Yeah? You'll start the transmission in a serial communication, asynchronous serial communication with a start bit. Easy. And when you started your communication, sent your message, you ended with a stop bit, or 1.5 stop bits, or 2 stop bits. This, I mean, what is half a bit? I know half a B, and it's called Eric, but half a bit, that's hard. Well, it came from teleprinters, and they had a mechanical flywheel, which was not that exact. So if you had the voltage state of a stop bit, you would stretch that out a little more so that it could synchronize with the flywheel again. This is why we have more than standard length bits, because the teleprinter is waiting and shivering in anticipation for that stop bit. Could it get worse? Yes. Yes, true, 1, whatever floats your boat. Have you seen the movie Tron? I hear a lot of 1 bits coming my way. That is awesome. So in Tron, the protagonist, Alan Bradley, encounters a character. And it's this one. It also looks like this. Two states. It's probably a bit. Well, Alan says, hold it right there. And the bit says, yes. What do you mean, yes?
Give it a
yes. So, is that all you can say? No? You probably guessed it. Yes, these are really spiky, I'll not throw them. And they morph in between those states, so that's fuzzy logic already. So now we have a bit with at least 4 states and something in between. I would say no bit is illegal. That also applies to yes bits, not only to no bits. And I insist no individual bit is illegal. And moving from bits to pieces, for example, pieces of text, we want to encode text. We had this BCD, these binary coded digits or decimals. Yeah, and we want to put some text on there. We have fractional bits left, we use them. Well, adding more signs like letters and a little bit of punctuation or something. It's originally by IBM, was also adopted by Honeywell and Burroughs and other companies. It's the original IBM 48-character BCDIC code. Odd layout, only capital letters. Well, it was used with punch cards, which had 40 characters, and this was a little bit extended. But punch cards have been around very much longer. 1725, when the first looms had patterns punched on paper tape to encode patterns in the fabric. So what if we want to extend that further? Well, we get EBCDIC, the extended binary coded decimal interchange code. It's a fixed length encoding which uses 8 bits. It was mostly used on IBM mainframes. Fixed length meaning all characters are the same length, disregarding wobbly bits. So same space on storage in memory. If we look at it in the most basic form, it's called the invariant subset. Meaning of these characters is defined here. They should, RFC 1980, should, 2142, yeah. They should remain in place and always use the same code. Well, should. Other variants fill that empty space with characters and more characters, and they occupy the same codes for different things. And those things, those variants, are called code pages. And the code page originally referred to the IBM manual where that character set was described, and the page number was the code page. Really, yeah. It was only with the release of PC-DOS 3.3, yes, these are originals, where that code page numbering system was brought to regular PCs, and the phrase code page was used for new commands and allow character encoding across all parts of the operating system. Some of the pages look like this, and the animation shows you some are vastly different, some are really close together and only change in a few things. EBCDIC has also been touted as a manifestation of purest evil, an encryption standard by the US government, though it is seriously just encoding, not encryption this time. Like really? And to depict incomprehensible language in a computer game named Zork 2. No. Other important encoding things around that same time and era. ASCII, the American Standard Code for Information Interchange. It was developed for teletype terminals, standardized in 1961. EBCDIC was invented before, standardized after, and IBM was a very strong proponent of ASCII, and it was on the board of development for ASCII. So why EBCDIC with IBM? Some would say lock-in, others would say time to market. They did not have time to build mainframes that would understand both or just run on ASCII. So yeah, history took a wrong turn. Since ASCII is now also a code page, it goes by these names if you ever encounter them. Yeah, I guess that's to make things easier. ASCII is a 7-bit encoding for 128 characters. Again, 8 bits in memory, 1 byte equals a character. It has control characters like bell, carriage return, and line feed. Bell is on a typewriter. When you get to the end of the line, it makes ding. Then you take the lever and return the carriage to its left position. Then you keep pressing, and then the paper feeds one line. That's why we still have these hex codes in files, unless specified otherwise in an RFC for MTA STS, I think. Yeah. So, what does it not define? Cursor control sequences like up, up, down, down, left, right. But BA is there. Printable characters like letters and interpunction. Basic ASCII character sheet. I'll not take a quiz on this with you. Don't worry. But comparing this with EBCDIC, it's vastly different. In ASCII, the characters from A to Z are in one sequence. In EBCDIC, they're not. The order of capital letters and small letters is different. That messes with your sorting. Have fun with databases or transferring of anything. No advanced math symbols, no Greek letters, no Cyrillic letters, no emoji. But what if you want to extend ASCII? There's a bit left, 128 to 255. Well, there's about 200 code pages for EBCDIC, about the same number for ASCII. So people thought, well, let's make an international standard to formalize a limited set of expansion, and that was ISO 8859. It supports most Western European languages with a Grand Prix de la Chanson d'Eurovision-like concept of Europe. It's also known as Latin 1, and there was Microsoft, and Microsoft being Microsoft, they had embraced Latin 1 for Windows. They extended it with more characters, and then they extinguished the idea in favor of their own proprietary Windows 1252 encoding, which is now the standard encoding in Windows. Also known by these other names, and speaking of standards, well, they're great. There's so many to choose from, and we should create one that works for everybody. Like Unicode, one standard to rule them all and in darkness bind them, to map all the characters in the world. It specifies the Unicode transformation format in UTF-8, 16 and 32 bits. It's most notably UTF-8 these days. It's a variable length encoding. So remember ASCII, the first bit was always a 0. So in UTF-8, the first bit of a single byte character is always a 0. So UTF-8 is 100% compatible with ASCII. That's great. You see characters and you cannot tell which it is because it's the same. You cannot make a mistake, which is great. And when you inspect the bits a little more and see, okay, The first one's 1, then we extend it. We have a leading byte, and there can be up to 3 following bytes, like 1, 2, 3 following bytes. And that allows us to be very efficient with encoding a lot of characters, most importantly, emoji. Yeah. So, but there's encoding, so there's problems. ASCII and EBCDIC are fundamentally incompatible. They have different code points for letters, for numbers, for everything. So you need to know, is this text I have EBCDIC or ASCII or something entirely different that we haven't even covered? Some special characters exist in one encoding, one family of those, and not in the other. So you might not be able to convert losslessly from one to the other. There's also code page problems because each one extends by over 200 variants. So on top of knowing ASCII or EBCDIC, you need to know which code page exactly to render that text correctly. It might end up with a t-shirt like that. That photo was taken 15 years ago and cropped to protect the innocent. It might mean Böse's encoding, or might have meant at some point in the production of this t-shirt. But isn't Unicode universal and meant to contain all the characters in the world? Well, there's some characters that are defined in EBCDIC code pages that do not exist in Unicode. Okay, now it's getting interesting, yeah? No individual character is illegal, but in UTF-8, some sequences of bits are illegal. Like, some bytes must never appear in UTF-8 encoded text. Or a continuation byte may never be at the start of a character boundary. It continues, it does not start, it says in the name. But some parsers, being parsers and doing semiosis and trying to analyze what they see, well, this allows us to inject characters and do overlong encodings up to 6 bytes, but those 2 bytes might end up somewhere. So I might be able to inject a null byte that terminates a string early, just in UTF-8. And the recommendation officially is to replace those characters that break and don't make sense and are not allowed with the Unicode replacement character. It replaces other characters. So this t-shirt is not misencoding, it's probably a security incident. We'll see. Well, some parsers allow illegal sequences. Okay, they might be buggy, or might this be intentional? Well, there's the WTF-8 encoding format. It does mean wobbly transformation format, not Windows transformation format, though it's only used by Windows. Because in UTF-8, the surrogates of UTF-16 are disallowed. Extension of characters is disallowed. But Windows allows those characters in file names. So Windows must be able to use illegal characters in file names. Sounds like a great concept to me. So Windows uses UTF-16 internally, cannot map these things properly by the standard, invents a new standard to break things. And this is why we have WTF-8. Yeah. So what is tooling that you can use to at least understand your pain with encoding? Let's see. There's the good old ASCII man page. If you run on a sane operating system that includes man pages, you can say man ASCII, you will get a man page with ASCII characters. That's often very helpful to have, like right from the comfort of your command line. There's also iconf. It supports different encodings. It can convert to and from. Which of those 100 to over 1,000 encoding types it supports varies widely by version number and operating system. So you might have only 120 ways or over 1,024 with alias names. There's also PyConf, because you cannot only rewrite things in Rust, you can also rewrite them in Perl. And PyConf is iconf written in Perl. Yeah, that's handy if you do Perl. There's also a tool called Encoding. It's also in Perl. It's deprecated. And if you didn't know there was a man page section N, now you do. There's more. And if you're not sure what a file is encoded in, there's encguess. Well, stop guessing. Let the guesswork be done by a computer. So that's why you can use encguess. And there's also uconf, which is similar to iconf, but it's written by IBM. It comes with the ICU package if you install that on your operating system, so that might help with EBCDIC, or it might not. I don't know. There's also a tool called CyberChef. If you're worried from the command line, it's not to be confused with CryptoChef with Vollbitverschlüsselung. Yeah, that website. It disappeared in 2014. Don't worry, it's not about encryption. It's about encoding. It's the Swiss Army knife for encoding things. It's a OCI container that you can easily self-host. It's open source if you trust software that's been written by the GCHQ, the British Secret Service. But if it's good enough for them, it might be good enough for you. If you know more tools that help with encoding, please post them on the interwebs so we can all benefit from our collective knowledge. And if you want to get creative with encoding, how about encoding your own information? Well, there's ways that encoding happens that you did not intend to. Is the information actually there, or can it be derived from that? Or can I use that information, combine it with something else, and then derive something from it? So that might not actually be there, the information, but you can still get to it. For example, if you want to exfiltrate some data from an air-gapped machine, get creative. Or if you're building side channel protections, we all heard these things about GPG private keys being derived from the coil wine of your power supply. That's a side channel, but somehow the information about what that key looks like ended up in the wee of your power supply. And somebody was able to figure out how to decode that back to that private key. Unintentional encoding. What about exfiltrating a private key with a CD-ROM drive? Yes, ROM, read-only memory. You can't just burn the thing onto a blank and take it with you. But some of those drives, they have a tray that can open and close. You have two distinct states. That's most bits. So, if you can open and close that tray, you can Morse or bit bang a key. Yep. So if you can watch that drive open and close, you can read that key back. But do you need to see that drive? No. A microphone in that room would be enough to hear the sounds that it makes with open and close, like slop, 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 slop. That would be enough. Do you need a microphone? No. Sound makes vibrations. Just put your phone with the vibration sensor app on the table of where that PC is and record the vibrations of that drive going into the end stop. You will find those bits. Get creative. Find new ways to encode data. Yeah. I already see those. Remove all the CD-ROM drives from air-gapped machines. Or, I mean, that might actually be practical. Removing keyboards. Keyboards have LEDs, like caps lock. It's the one you use on the internet for shouting. It has an LED that lights up. Some keyboards also have a numpad thing if you want to shout in numbers. You have two LEDs. You can be twice as fast. Now your threat model contains RGB on a gaming keyboard. Have fun with that. And since we're at BalCCon, and I know most of you have been exposed to encoding in their childhood. I want to help you to relive those moments, and you can get your very own BalCCon2k25 logo as a paint by numbers and draw your own if you so intended. I have a few with me. There's colorful things to paint if you like. If there's not enough, we can make more, or I can send you a PDF so you can paint your own. And with that, I'd like to say thank you to all the volunteers who keep this whole show running for days and in preparation up to the event and tearing it down. So thanks to you, all the volunteers here who do a great job with running this conference. This is your applause. Also, thanks to Milopit and Jelena for bringing so many skilled and interesting people to BalCCon every year, who bring their friends now and share the knowledge in these rooms and have fun together. I'd also like to thank a few people who have helped me with the impossible endeavor of doing a philosophical track at BalCCon. That is Columbia for expert knowledge in graphics and design and helping with she did the paint by numbers logo thing. Krisi for expert knowledge in linguistics, semantics and semiotics. Mladen for native language with Srpski, which helped me a lot to understand a few things. Pluvia for music encoding and library archival of data. And Fishy for biological misinformation that is spread by orchids to lure bees in. I'm not sure if we have time for questions. My timer says we have, but my slide says I'm not sure I need to ask.
Yes.
It's your call. Okay, we do have time for questions, so please bring them up in a way that I may be able to decode them.
So please raise your hand, and I will come to you with the microphone. First of all, let's give up an applause to MacLemon. Enough. First question. Okay.
I thought I had scared them.
What about Shannon?
Shannon, yeah, Shannon's law of entropy, you mean?
Of encoding and symbols and transmission and recipient and sender.
Come to my talk next year about compression. I'll probably have Shannon in there. About information theory and yeah.
Next one. Wave? No? Okay, then
I successfully scared him.
I have a challenge for you. So you can't see the number of slides MacLemon has. If you can guess
you
it.
can have a peek here.
No, I know. I know it. I think they don't know. So if you can guess it, if you can, like, at most to like 20, by making a mistake of less than 20, I will give you a special thing that I carry around this gun holster, and you can share it with your friends. So.
The answer needs to be decimal.
Yes. Thank you for that clarification. Okay. Guesses?
69.
276, you? Okay, that's wrong.
280 something.
Too far away. Any more guesses? 328? No? No.
No. But
No?
90.
Come on, I really want to.
I can add something to the numbers that have been shouted. 96 is the number of characters in ASCII that are common to most code pages. 256 we covered already with the Swiss Railways. More numbers?
Okay, yeah, more numbers. I will. How many?
46.
The more. So he's been going on for an hour. 400, less than that. Less.
256.
That has already been guessed.
That has been guessed.
128? No, more than that. 170, more than that.
Okay, let's guess the number.
20? 220 is the closest. Any more guesses? 190. Ooh. Okay, who said 190? Who said 190? Okay, you're the first, so I choose you as the winner because we don't have too much time, and this is what you get. Enjoy. And I think we can wrap it up here. Let's give MacLemon one more applause.